This lecture is about proof terms for first-order logic. So previously, we have developed this natural deduction system for first-order logic by introducing this universal quantification and existential quantification. This time, we would like to apply Curry-Hall isomorphism to these four inference rules to derive proof terms for universal quantification and existential quantification, and also the corresponding beta reductions and eta expansion. So let's see the details. So first, we'd like to observe that terms can appear in both types or propositions, because the types are equivalent to propositions and proof terms. So here's an example. Suppose that we have a proposition or type equality 0, 0, where this EQ is predicate symbol, and these are terms. Suppose that there is a proof term for this proposition or this type. So we can use these types and propositions interchangeably. And intuitively, this proof term should contain this proof term, actually term 0 somewhere, because this proof term is a proof or representation of a proof that 0 is equal to itself. So this proof term describes a property of a particular term 0. So we'd expect that this proof term contains term 0. So now we see that the same term 0 appears inside the proof term and also inside a type or proposition. That's the first observation we make about first-order logic. Now, let's discuss the for all introduction rule and then convert it to typing rule. So this is the for all introduction rule for all XA. This is for all introduction rule. We introduce a fresh parameter, and then, so in order to prove this, we substitute A for XA for a fresh parameter A. So this inference rule is the introduction rule for universal quantification. But now we'd like to reformulate this inference rule in terms of a proof term. So this judgment disappears, and we are supposed to find the proof terms. But according to the observation we made here, if this proof term proves a property of a specific term 0, perhaps this proof term contains 0 somewhere. So similarly, now this type is about a specific term A, a parameter A. So perhaps this proof term contains this proof term contains term A somewhere. So perhaps this proof term would look like this. Now the question is, what is the right form of proof term? So as far as this proof term conveys everything that is contained in the premise, we may choose any syntax for this one. But we'd like to use this syntax because we introduced this new term variable. We'd like to use Lambda Abstraction using the same term variable. So remember that a term can appear both in proof terms and also in types. So this term variable appears in proof terms and also in types. And then what we do is to make a copy of this proof term over here and replace a with the variable x. So that's the new proof term that we'd like to assign here. So to generalize this one, we can think of it as, suppose that we have these two types. This is for introduction rule, and we could rewrite this proof term as some term m where x has been replaced by a. So in other words, we'd like to write m here. Then the lambda abstraction can be written as this form. So this m perhaps contains so this is m, and this m contains somewhere this term variable x, and we made a copy of it and then replaced x by a. That's what we did. So we made a copy of this one over here and then replaced x with a. That's all. So this is for all introduction rule, and we decided to use the same almost the same syntax, which is lambda abstraction, to represent the proof of this type. And there's a good reason that we use this lambda abstraction, because it's really a function which takes a proof, which takes a term x, it takes x, and then returns a proof that a it takes a term x and then returns a proof that x satisfies a. So in this regard, we can think of it as really a function taking a term and then returning a proof term. So that's the reason that we'd like to reuse the syntax, this lambda binder. So that's a full introduction rule. Now let's talk about for all elimination rule. The inference rule dealing with the truth judgment looks like this. You have a for all a true, then apply for all elimination rule, and you can substitute any term. So term x for term variable, term t for variable x in a. So that's the for all elimination rule. Now let's reinterpret this inference rule in terms of proof terms. So this disappears, and we are going to find a proof term here. So suppose that proof term m has this type, and whatever proof term comes here should carry first proof term m, because we have to represent the proof in the premise here, and then we should contain term t here, because that's the decision that we made here. We decided to replace this term variable x with a particular term t. So there should be so this decision should be contained somewhere in this proof term. And just because we decided to use this lambda abstraction, lambda binder, for the syntax of this proof term, we'd like to use the corresponding syntax, which is lambda application. So that's all. So to summarize, for this For this universal quantification, we have introduced the two new proof terms, which is lambda and lambda application. It's almost like the previous lambda binder, except that this time the variable ranges over terms, not proof terms. Similarly, the argument is not going to be proof terms, rather the arguments are terms. So that's the difference. So we have derived these two inference rules. Now let's talk about this existential quantification. The first introduction rule. So this is the introduction rule for existential quantification. So existence A is true if you can find a concrete witness T for which A is true. So this is the existential introduction rule. Now let's reformulate this inference rule in terms of proof terms. So this true disappears, and we'd like to find the proof terms here. Suppose that a proof term M has this type, or it proves the truth of this proposition. Now the question is, what should we provide inside this new proof term in the conclusion? So needless to say, we have to put M somewhere. We have to carry this proof term over here. But in addition, a critical decision that we made here is we decided to use term T as witness. It's a crucial, that's important decision that we made here in the course of proving the truth of this proposition. And also that's the essence of constructive interpretation of existential quantification, where you should actually present a witness T. So we have to carry not just this proof term M, but also we have to carry the concrete witness that we used to prove this existential quantification. So we can use any syntax for this proof term as far as this proof term contains both proof term M and witness T. And we'd like to use this syntax pair using this bracket, first witness T and then proof term M. So intuitively you can read this proof term as, to prove this existence X at A, I have discovered a suitable term witness T, and this M is going to actually prove that T satisfies this property A. So that is, M is going to have type A, where X has been replaced by T. Okay, that's the existential introduction rule. Now let's discuss the existential elimination rule. So previously, the inference rule looked like existential elimination rule. So we have existence X A true, and then we'd like to eliminate it, but we don't have any clue about what is the actual witness for this term variable X. So you have to just introduce a fresh parameter A. So now we assume some term, an arbitrary term about which we know nothing, and its name is going to be A. So we assume that this term A satisfies this property A. So we assume, so we introduce hypothesis W labeled with a W, and then it proves A for XA true. So in other words, this parameter A satisfies this property A, this property capital A. And then if we prove C true, then you can always prove C true. So an important property in this inference rule is A is not supposed to appear inside C. So in other words, the scope of this term parameter is limited to this derivation tree. But once you leave the premise, its scope is lost. So this proposition or this type C is not supposed to contain A. Okay, that's an important observation that we have to make. Now let's get rid of this keyword true and then reinterpret everything in terms of proof terms. So suppose that we have proof term M, which proves this proposition, or this proof term M has this type. And now we make an assumption that this is true, or there exists some proof term of this type. But this is a hypothesis, so we don't actually have a proof term of this type. It's just a hypothesis. So we have to introduce a proof term variable, and we'd like to reuse this label. So let's just say this is W, and we don't need this one anymore. Now, the question is, what does this proof term look like? So remember that the scope of parameter A is limited to this derivation tree. So therefore, C escapes this premise. So therefore, A is not supposed to be found inside the C. So that's a fact. On the other hand, it's okay to use parameter A inside this proof term. So it may not be clear at first, but let me show you an example. Let's just say W has a type equality A, comma A. So this proposition is expanded to this one. So we have this hypothesis. And then as an example of this type C, let me find a type here that does not contain without A, but a proof term using this parameter A. A simple example is this one. We have evidence that equality A and A is true, so A is equal to itself. So therefore, we have just proven that existence X equality X is true, because we have just found the witness. The witness for this existential quantification is this parameter A. We know that there is a witness, a concrete term A. And the proof term is going to be, first, well, you have to present the witness and then the proof term for this particular witness. So the witness is A, and the proof term for this particular witness A is W. So we see that Inside this proof term, it's okay to use A. It's not going to escape the premise. But inside this type, you are not supposed to use A. So here, this is an example. So as illustrated in this example, it's okay to expect instances of this parameter A inside this proof term. But A is not supposed to be found inside this type C. Then the question now is, what kind of proof term should we expect here? And again, even though this proof term may contain this parameter A, the conclusion, whether this is a proof term or this type, we are not supposed to use this parameter again in this conclusion. Okay, so the story goes like this. We imagine that originally this proof term has term variable x, and it has been replaced with a. So perhaps we can rewrite this proof term as something like this is x, and this one has been replaced with a. So it's confusing. Let me move it over here. So we have proof term m of type existence x of a. And this proof term in general can be rewritten as some proof term where x has been replaced by a. Because this proof term may contain a. Now we use this form. Let's assume that this proof term m can be, let's assume this proof term m can be deconstructed into a witness x, and then its proof w. And then we may use this proof term, which is a copy of this part, to prove C. So the story goes like this. If we interpret this derivation tree, it says basically this term A satisfies C. Now let's replace this one as just x. Then if you replace x, or if you just take this part, then it's going to be proof that C is true. So now let me write this one as proof term n. So let me erase it. Let me erase it, and then just write the C, n. Then we would have n here. Remember that this proof term n, of course, may contain term variable x. And moreover, this proof term n may contain not just the term variable x, but also proof term variable w. Because we started with this variable w. So it goes without saying that this proof term m may use this variable x as many times as it needs. So this is the existential elimination rule. It looks quite complicated, but the story goes like this. We have proof that there is some term x which satisfies A. So let's assume that the witness is x, and let's say the proof is represented compactly with this variable w. And then we see that this proof term N proves C, where this proof term N may use both X and W. So this is the elimination rule proof term that we derive from the elimination rule. So let me move it. So let me move over here. So this is the reinterpretation of this elimination rule. So now we have devised a new form of proof term corresponding to existing elimination rule. So we have finished the discussion of these two inference rules. Now let's try to derive these beta reductions and eta expansions. And the strategy is just the same as before. Well, this beta reduction, it always takes a detour intro followed by ln, and then we try to get rid of this detour. So here we have introduction, elimination, and then we try to get rid of this detour. And expansion starts with a proof term of given type, and then we'd like to reconstruct it by exploiting this one. And the pattern goes like this. So let's try to derive this beta reduction. So beta reduction takes a detour. So for all introduction rule, so we have for all xa, and the premise is going to be a for x. So we have a true here, truth judgment. But we will actually get rid of this truth judgment, but instead try to find the proof term. So we introduce fresh parameter a. And then what about for all elimination rule? You can use any term for this term variable x. So you have t for x a. And the introduction rule looks like this. This is a lambda abstraction. So lambda x dot m, where m has been replaced, x has been replaced with this a. And this one is lambda xm applied to its argument t. So the question now is, how can we better reduce this derivation tree? The goal is we'd like to find a proof term of the same type. So we'd like to find a proof term of the same type, but without taking this detour. So the idea is we have almost found a proof of this one, except that x is replaced by a, not t. So the idea is if we apply substitution t for a, the entire derivation tree here. So in other words, we apply, suppose that this is proof D, then we apply this substitution to the entire derivation tree D. Then we have to apply A for T here as well. Then A is replaced by A, and A is replaced by T again. So in effect, we replace X by T. So we get this one. And then this one also follows the same pattern. X goes to A, and A goes to T. So in the end, you have X for T. And this is precisely what we would expect from beta reduction of lambda application. So without looking at this whole core details, if you are given this lambda application, you would expect it would reduce to this term, this proof term. And that's precisely the result of this beta reduction. So that's the beta reduction for all quantification. And what about the Eta expansion? In the case of Eta expansion or local expansion, you start with a proof term of this universal quantification. And the question is, how can we obtain another proof term of the same type by exploiting this one? And the strategy is we apply elimination rule and then apply introduction rule again to find the proof term of the same type. So we have this proof term M of type X for all X at A. And then, but in order to prove this one, we would eventually apply for all introduction rule. So with the parameter A, then this one would be X for, A for X in A. Then in order to go this way, it's just a matter of applying for elimination rule with this term A. So let's replace this X with A, then we would have M where X has been replaced with A. Now that's precisely the pattern that complies with the for all introduction rule. So I got confused. This is for all elimination rule. So you actually have to apply this M to A because perhaps M is going to be some lambda of this form. So now you have to apply this lambda to a concrete term M, a concrete term A. So now the pattern complies with the default introduction rule. So you introduce lambda X and X. So actually there is no difference. It's almost similar to, almost like the Eta expansion for the previous form of a lambda, except that we are dealing with term variables. So to summarize, we have this one. If M has for all X A, it Eta expands lambda X M X. So there's nothing surprising here. Now let's discuss the beta reduction and Eta expansion for existential quantification. Existential quantification, the introduction rule looks like existential x dot A if you can find term T for x in A. So this is existential introduction rule. And suppose that there is a proof term of this type. Then we have just found a witness T and a proof term M, which proves existential XA. So that's for existential introduction rule. Now let's eliminate it. This is the existential elimination rule. We introduce a fresh parameter A. So now this becomes A. So we have A for X in A. And this hypothesis is now it's a W. So we introduce W here. And then eventually we prove some proposition C. But remember that this one actually may use this term A, as we have seen in the previous example. So it looks a bit complicated, but let's rewrite this proof term as N, where X has been replaced with A, because we have to carry this N over here. Then the proof term is, we assume that the witness is X. not A, because we cannot use A anymore here. So we assume that the witness is X, and the proof that witness X satisfies some property is a W. So W comes from here, and then we can show that N has a type C. So this is the existential elimination rule. Now the question is, how can we better reduce this one? So we have to find another proof term C without taking. We have to find the proof term of the same type without taking this detour. Detour consisting of this existential introduction rule and existential elimination rule. And the idea is we have almost found a proof term of type C here, except that we have this hypothesis. So now the problem reduces to getting rid of this hypothesis. If we can replace this hypothesis with the actual concrete proof term, then we are finished. And we can replace this hypothesis by exploiting this proof, this derivation tree or this proof term. So I'm going to compose. So I'm going to compose this one and this derivation tree to build a new proof term of type C. So the idea is we are going to substitute this one over here. Problem is this proof term has type T for XA, whereas this hypothesis W has A for XA. So there is difference between these two types. So in order to be able to substitute this proof term for W, we have to either change T into A, or the other way, A into T, so that these two types would match each other. And changing A to T is simpler because this is the parameter. So the plan now is I'm going to make a copy of this one over here. Okay, so we have a copy. A for X and C, W, A for X, A. So I have just made a copy over here. And then I apply this substitution T for A to the entire derivation tree. Then what happens? Basically, you replace A with this term T. So this becomes T, and this becomes T. Now you can directly substitute this one. So now it's just a matter of replacing W with M. Okay, so let's again apply this substitution this time. M for W. Okay, let's apply M for W to the entire derivation tree. Then W becomes M, and you have to apply M for W. And then this type matches precisely the type shown over here. So now you can actually copy this one over here. In this way, we have built a proof term of type C without taking detour, and the answer is this one. And this precisely reflects our intuitive reading, the intuition behind this left binding. So without without knowing anything about this existential quantification, if somebody is presented with this left binding P for Tm in C, he would instinctively beta reduce it into N, where X is replaced with T and W is replaced with proof term M. That's precisely what we have discovered here. So this is the beta reduction for existential quantification. And finally, there is Eta expansion. So Eta expansion is actually, we can actually derive the Eta expansion using derivation trees. But it's a good exercise to directly derive it. This exercise helps you to better understand this new form of a proof term. So suppose that we have a proof that there is a term X which satisfies A. So now let's say from this proof term M, we know that there exists term X, and we know that this term X satisfies property A, and let's just say the proof term is W. We don't know the actual proof term, but we know that there is a proof term. So let's just say it is W. And then we are supposed to rebuild. We have to find another proof term of the same type, this one. But we have already found such a term, witness. What is the witness? It's X. And what's the proof? It's W. So you just pair them up again, and then you can show that it has a type, this existential type. So that's the Eta expansion of this existential quantification. So in this lecture, we have revisited these inference rules formulated in the natural deduction style, but using truth judgment, and then reformulated it using proof terms. And then we introduced these new forms of proof terms and also beta reduction and Eta expansion. There's nothing particularly surprising here. We just applied the Curry-Horde isomorphism in a systematic way, although it was a bit more complicated, in particular this existential quantification. But if you go back to all the derivations, you will realize that there's nothing particularly strange. Everything is actually quite simple. You just apply Curry-Horde isomorphism and then systematically convert all these inference rules into these typing rules, and then you can derive this beta reduction and Eta expansions.